Hi, it's Mr. T here. In this video, we're going to go over how we might write a report on oxidation-reduction equation. So this is particularly important if we're going to carry out the NCEA Internal Achievement Standard 91167, but also it's got lots of interesting points if you want to become more familiar with oxidation and reduction reactions. This report for each of the two reactions I'm going to carry out includes the following three major components. The first one is identifying oxidation and reduction, or the reductant and the oxidant, in terms of both the change in oxidation number and the loss or gain of electrons. The second point is going to be that we're going to, in this report, relate what we observe to the species that are present, or the species at the start, or the species produced in the reactions. And the final thing we're going to have to be able to do is write balanced half and overall equations. So we'll be going over all of these 3 points in this video. So on this slide here, we're going to give a demonstration of what the practical might look like if you carried it out. In this practical, we're reacting two things together. We're going to put them in a test tube. So the first thing that we're adding is dilute hydrochloric acid. We're going to add 2 mils of it, 3 mils, sorry. Then we're going to add one small piece of zinc metal. Now the small piece of zinc metal is a grey solid. And we're going to observe the reaction. What we notice is that some colourless bubbles come off, and the zinc solid gets smaller and disappears. Now the original dilute hydrochloric acid solution was colourless. The zinc metal was a grey solid, and the final solution is colourless, and it had colourless bubbles. Now these last three observations we're going to use to construct our report to show how we know oxidation and reduction was happening, what was being oxidized and reduced, and how we can link what has been reacted and produced to the observations that we noted. So the first thing I'm going to do is go on to the next slide. So in this next slide, this is reaction A. Here is a list of the observations that we just went through in the previous slide. So what we have here is we have dilute hydrochloric acid. Now because this is dilute acid, actually the reason that it's hydrochloric acid is not important. If it was dilute sulfuric acid or dilute nitric acid, it would have the same ion that we start with, and that's this positive hydrogen ion. And if we remember that positive hydrogen ions can be changed into hydrogen gas. Now, how did we know that this was going to be changed into hydrogen gas? In this case, we knew it was going to change into hydrogen gas because we saw some gas. We had some dilute acid and we saw some gas. So we're going to start with our reactant, go to our product. Let's put the states in next to each of these. So the ion here on the left-hand side is aqueous, and on the right-hand side, the H2 was the gas that was produced. So this is good. So we now have the states of each of these. The second thing is, what were the colors of these? So dilute acid, or H+, the original solution was colorless, so this must be colorless. And the H2 bubbles, the bubbles of gas, were also colorless, so this is colorless as well. So we've identified the state of each of these two, and we've identified the colors of them. Now, if you are carrying out the achievement standard 91167, they will give you a resource sheet that has the name and the symbol and the color of each of these species in the solution. So if you weren't sure what dilute acid is, you look up the name, you find its symbol, and you find its color, and you write it down. So we've done that. So now we're going to balance the half equation. Now we're going to use the ion-electron method. That is that we balance the atoms that aren't hydrogen first, then we balance, hydrogen or oxygen, then we balance the atoms that are oxygen, or the oxygen atoms, by adding water. Thirdly, we balance the hydrogen atoms by adding H+, and then fourthly, we balance the charge. In this case, there are no atoms that aren't hydrogen, no atoms that aren't oxygen. So we're balancing the hydrogens. We're going to add another H plus to the left hand side, so we've got 2 on each side, so we put a 2 in front of the H plus. Now electrons have jumped the gun here. We see on the left hand side that we have a positive 2 charge, and the right hand side is no charge. The electrons are always added to the most positive side, so we're going to add electrons. But because the charge initially on the left hand side is +2 and the charge on the right is 0, we're going to add 2 electrons to make sure that this has the charge balanced. So now we have our balanced half equation. The next thing we're going to do is we're going to identify, is this half equation an oxidation equation or a reduction equation? Now what we can see here is that, so when we write this, we're going to write in terms of the reactant on the left hand side. This is the H plus, and we need to identify, are the electrons being gained or lost? If the electrons are added to the left hand side, they're being gained. Now we need to remember that when we gain electrons, it's reduction, lose electrons, it's oxidation. In this case, the hydrogen ions are gaining electrons. In fact, one hydrogen ion gains 1 electron. So if 2 hydrogen ions gain 2 electrons, we can say that it's true that a hydrogen ion gains 1 electron. So gaining electrons, this is going to be reduction. This is a reduction half equation. I'm going to justify why it's a reduction half equation. This is a reduction half equation because the reactant, this species here, the H plus, is reduced as each H plus ion gains 1 electron. Now I'm going to specify exactly how many electrons the reactant gains. Okay, that's really important. Also, when I talk about the different species, I'm going to put in brackets what state they're in. This is an ion in solution, so it's going to be aqueous, AQ. We can also justify that this is a reduction equation using the oxidation states or the oxidation numbers. So if we calculate the oxidation states or numbers, now if you need to catch up on that, there's a link here in the video about now to another video where I've gone over how to calculate oxidation states. Now, so the oxidation state of H plus is 1 plus 1, and the oxidation state of H2 is 0. H plus is +1 because this is an ion, a monatomic ion, an ion made of 1 atom. So its oxidation number is equal to its charge. The oxidation state of H2, this is an element, and an oxidation number of an atom in an element is 0. So what we can see is that the oxidation number is going from +1 to 0. It's decreasing, so it is reduction. We can state this, but we're actually going to be more detailed here. We're going to state the following. H plus is reduced as the oxidation number of the hydrogen atom, that's what we identified here, is +1 in the H plus. Sorry, it decreases from +1 in H plus to 0 in H2. So if I was to write my explanation using oxidation numbers as to why this is reduction, the hydrogen ion is reduced as the oxidation number of the hydrogen atom decreases from -1 in H plus aqueous to 0 in H2 gas. This, if we are carrying out this achievement standard, the balanced equation with the explanation as to why it's reduction is needed. If we just say that we have gained electrons, that's at achieved level. If we can specifically say how many electrons we gain for each reactant, then that's a merit level. We can also use the oxidation number argument as another example to explain how we know it's oxidation or reduction, and we need that for a merit level as an alternative for the other. So we've carried out all 4 of these things. We're now going to go and then justify the other reactants. So we had 2 reactants here. We had dilute hydrochloric acid, and we had a small piece of grey metal, the zinc metal. So let's look at that one. So small piece of grey zinc metal, that's going to, if we have our resource, we're going to look and we're going to find we have a zinc as one of our species. And of course the zinc is going to turn into zinc 2+. When we're looking to what an species turns into, it's going to turn into something that's similar to it. So if we had the table of all the different species involved in oxidation reduction with their colors and their names, we can find that zinc metal is Zn, and the species that pairs with it is Zn2+. Now Zn we know is a metal, so therefore it's a solid, and we're going to put down its state as S. Now because Zn2+ is an ion, this is going to be dissolved in the water and the solution, or it's going to be aqueous. We're going to put brackets AQ. If we go back to our table again, all we can remember, zinc metal is grey and zinc 2+ is colourless. Now we've identified the state and the colour of each of these. We're going to balance. On the left hand side we have no charge, and on the right hand side we have a +2 charge. We add electrons to the side that has the most positive charge. We're going to add them to the right hand side. We need to add 2 electrons to cancel out the +2 charge. So this is our fully balanced equation. The next step we're going to do is we're going to justify whether this, we're going to say whether this is oxidation or reduction, and then justify it using the loss or gain of electrons and the ion-electron method. So this is oxidation because it is losing electrons. If there's electrons plus electrons on the right, then the reactant has lost these electrons. It's lost 2 electrons. So this is an oxidation half equation. The reactant on the left has been oxidized as each of these Zn solids loses 2 electrons. Now you could also write this in the form that zinc is a reductant as each zinc loses 2 electrons, if you're comfortable using the terminology reductant instead of saying something is oxidized. The next step we do is we're going to use oxidation numbers. The oxidation number for zinc, because it's an element, is 0, and for zinc 2+, its oxidation number is +2. If we are going to justify using oxidation numbers, we're going to say that the zinc metal or zinc solid here is oxidized because the oxidation number of the zinc atom in both of these changes from 0 in the zinc metal to +2 in the zinc ion. If you're writing down this explanation, make sure you're specific. You say what the oxidation number is and what is the species it's in. It's 0 in zinc solid to 2 in zinc 2+. Okay, so it's increased, so this is oxidation. So now we've actually covered all 4 of these points. We've identified the reactants and products. We've identified their states, colors. We've balanced the half equations, and we've justified whether they're oxidation and reduction. We then are going to go on to the last 2 points we need for this report. The 2 points are the following. We need to balance the full equation, and we need to link the observations of the reactions to the species involved. So to balance the full equation, I'm going to write down the 2 half equations here. You should already have these written down if you've done the previous 2 parts of the report. Notice that the zinc half equation and the dilute acid half equation both have 2 electrons on them. Now, if we are doing an oxidation-reduction reaction, we would expect to have electrons on the right-hand side in one of the half equations and electrons on the left-hand side in the other. Now, the number of electrons is not always equal, but in this case it is. What that means is that these 2 half equations can add straight together, and we can cancel the 2 electrons out. Because, of course, this equation here, the hydrogen ion is donating, the zinc equation is donating 2 electrons to the hydrogen ion, so it can become a hydrogen gas. There's an exchange of electrons. That's what's happening in oxidation reduction equations. So we're going to add the full equation. It does not matter which order you write down your reactants or the order of the products. So here we go, zinc solid plus 2 hydrogen ions in solution, aqueous, go to zinc ions in solution plus hydrogen gas. Now, so I remember, because I'm about to link the observations to the overall reaction, I'm just going to write the colors under this overall equation again. And now I'm going to write a final overall explanation why I noticed the colors that I had. And that's going to be the original zinc was grey because zinc metal was grey. The dilute acid was colorless because the H plus is colorless. The final solution ended up being a colorless solution with bubbles because both the zinc 2+ ions and the hydrogen gas is colorless. And the gas bubbles are produced because we had the hydrogen 2 gas. That's why we observed them. So we write this down and we've finished our report. We've covered all aspects of our report. We've written a fully balanced equation. We've linked the colors to the species present. And on the previous 2 slides, we carried out the explanation as to why one equation here, the loss of electrons is oxidation, and the bottom one is reduction. I hope you found this useful. I'm going to go over another reaction, reaction B, in the next video. Make sure that you have a look at that as well to go over it. But thanks for listening, and look out for the other videos I've done on oxidation and reduction.